Okay, welcome back everyone. In this example, we're going to be looking at conservation of energy, and this is number 63 from chapter 7. And so basically what you've got is a circular hill that someone is skiing on, and we want to find the point on the hill where the skier basically loses contact with the hill. So in other words, we're looking for the angle at which the normal force goes to zero. And so it turns out that we're going to have to attack this problem by using both forces and conservation of energy. So the first thing we'll do is we'll look at the point where contact is lost, and we'll draw in gravity, mg, and the normal force, F normal. And it's a frictionless surface, so this is basically it. So what we can do here is take gravity and decompose it into two components, and so that gives us an angle alpha right here, and so we would have a force of gravity tangent to the circle, which is FGT, and that's going to be mg sine alpha, and then we'll also have a force of gravity which is radial, so the pointing inward part, FGR, and that's going to be equal to mg cosine alpha. And so we can make use of centripetal force, and we can say that the net force in the centripetal or radial direction is going to be equal to mv squared over r. Because the skier will definitely have a speed at that point, we just don't know what it is. So we can write this and realize that inwards forces are always positive, so Fg radial minus F normal is equal to mv squared over r. I'll do a capital R for the radius. Keep things consistent. So the normal force is actually going to cancel out, and Fg radial we said is going to be mg cosine alpha. Well, it looks like what we have here is one equation but two unknowns, alpha and v. And so what we have to do is apply a second equation, and so we're going to do this with conservation of energy, and you'll see why we do this in a moment. But let's make the top of the hill our 0 point, a height of 0. And then that means that we need to find this height. Okay, now let's zoom in on this a little bit so we can see what's going on. Well, what we have is this entire thing is the radius r. And we also have that this segment is the radius r, which means that this side is r cosine alpha, which means that the tiny little green portion is r times 1 minus cosine alpha. And so you can check that. It's kind of similar to some pendulum problems we've seen already. And what this will do for us is it will give us a final height. Well, our initial height is going to be 0 because we're starting at the top of the hill. But our final height is going to be negative r 1 minus cosine alpha. And this is important when we apply conservation of mechanical energy. So conservation of mechanical energy tells us, one way that we could write it is that the total change in energy is 0. So the change in kinetic plus the change in potential is equal to 0. Or any change in kinetic is equal to the opposite of the change in potential. And in this problem we're just dealing with the potential due to gravity. And so we could write K final minus K initial is equal to negative mg H final, because we have U final minus U initial, and U initial is 0. And likewise, K initial is 0, and K final will be 1/2 mv squared. Well, that's good because there's our mv squared. That'll get us m. And then we can just write negative mg, and then the height final comes from here. It'll be negative r 1 minus cosine of alpha. So we can get rid of those negatives, and there's a couple different ways to solve this, but probably the most straightforward is to say that mv squared over r is equal to 2 mg times the quantity 1 minus cosine alpha. And so then what you see is that we can substitute this directly up here for mv squared over r. And so what we get is that mg cosine alpha is equal to 2 mg minus 2 mg cosine alpha. Well, we can get rid of our mg's, and so what we're left with is 3 cosine alpha is equal to 2, so the cosine of alpha is 2/3, and that gives us alpha of about 48.2 degrees. And that, in fact, is the angle measured from the vertical when the skier will lose contact. In other words, that's where the normal force goes to 0. So you see in this example that sometimes we have to put together many different ideas. In this one, we had to look at the forces involved, and then we also had to look at the potential and kinetic energy involved.